Okay, so we're going to learn how to represent the decimal number 64.2 in IEEE 754 standard single precision floating point format. The first thing to note is that single precision IEEE format, it takes 4 bytes or 32 bits, and there are 3 components represented in those 32 bits. The most significant bit is the sign bit, and that is at index 31, followed by the exponent, which is 8 bits and indices 30 through 23, and then the fraction part, which takes up 23 bits and is the indices 22 to 0. And then it's also important to note that the bias value is 127 for IEEE 754 standard single precision. So there are 5 steps to obtain the sign, exponent, and mantissa, or F. The first step is to get a binary representation of 64.2 with the number of bits for the F field plus 1. So the F field would be 23 fraction right here, and we need to get one more than that in the first step, so that's 24. So we'll first find the integer representation of 64.2. So then we start by dividing 64 by 2. That equals 32 plus a remainder of 0 over 2. So then we bring 32 down. So 32 divided by 2 is equal to 16 plus 0 over 2. Bring 16 down. Divided by 2 is equal to 8 plus 0 over 2. Bring 8 down. So 8 divided by 2 is equal to 4 plus 0 over 2. And then bring the 4 down. So 4 divided by 2 is equal to 2 plus 0 over 2. Bring the 2 down. That's equal to 0. That's equal to 1 plus 0 over 2. And lastly, bring the 1 down. 1 divided by 2 is equal to 0 plus 1 over 2. Then we can stop now because we've reached 0 in the quotient part. So then for the remainder parts, 0, 0, 0, 0, 0, 0, and 1, we can now make up the integer part of the binary representation of 64.2 by bringing this to be the least significant bit, this to be the next least significant bit, and so on. Okay, so that's 64 represented in binary. Now we need to find 0.2 represented in binary. So then we start with 0.2 and then we multiply it by 2. That equals 0.4. Then we bring 0.4 down. No, that's not the whole number. That's just this part of the number. Then we say times 2 is equal to 0.8. Then we bring 0.8 down. 0.8 times 2 is equal to 1.6. Bring the 0.6 down, not the 1. 0.6 times 2 is equal to 1.2. Bring the 0.2 down. 0.2 times 2 is equal to 0.4. Then we bring the 0.4 down, so 0.4 times 2 is equal to 0.8. But we have a repeating pattern here, 0, 0, 1, 1, and then we start with 0.2 again, so the pattern will repeat. And then note, for the decimal part of the binary representation, in the integer part we brought the first number, the first remainder to be the least significant bit. Here we bring the number to the left of the decimal point to be the most significant bit of the decimal representation part. So this will come to be 0, decimal point goes right there, 0. Then we bring this, bring it here, this one here, this one here. And note that the pattern will repeat after this. So then 64.2 in binary will be represented in, again, 24 bits like we had specified, will be 1 0 0 0 0 0 0. So this will be 7 bits right here. So then the point right there, we need to fill up the rest of the 24 bits with the repeating pattern 0 0 1 1. So we'll go 0 0 1 1 0 0 1 1 0 0 1 1 0 0 1 1. That's 16 plus 7, which is 4. It's 23. So then we'll go 0. And then, yeah, so this is 24 bits. So now we need to, the next step is to normalize the binary representation of 64.2 to make sure that there's a single 1 to the left of the binary point. So we can copy this value and paste it here. And all that it means by normalize is to move this decimal point till there's a single 1 to the left of the binary point. So that will give us this value right there. But now we can note how many times that we moved the decimal point. So 1, 2, 3, 4, 5, 6. So then this will be, so this value above is equal to this value below times 2 to the 6th. And that's all it means by normalizing. So now we can note that since we use 23 bits for the mantissa in a single precision IEEE representation, and since there's always a 1 to the left of the binary point when we normalize the value, we don't need to store this hidden bit in our final representation. So step 3 is to find the 8-bit biased 127 representation of the true exponent e, which was 6, to obtain the biased exponent uppercase e. So we say 6 plus 127, that is 133. And now we just need to find 133 represented in 8 bits, following the same procedure that we did for 64. So that'll be so then we bring the 66 down. 66 divided by 2 is equal to 33 plus 0 over 2. 33 divided by 2 is equal to 16 plus 1 over 2. Bring the 16 down. 16 divided by 2 is equal to 8 plus 0 over 2. 8 divided by 2 is equal to 4 plus 0 over 2. Just shrink this down a little bit. Then we go 4, bring the 4 down. 4 divided by 2 is equal to 2 plus 0 over 2. Bring the 2 down. 2 divided by 2 is equal to 1 plus 0 over 2. Then lastly, 1 divided by 2 is equal to 0 plus 1 over 2. Then we have these values in the remainder part. It's 1, 0, 1, 0, 0, 0, 0, 1. That's our capital E for our IEEE representation. So then step 4 is to simply get the 23-bit mantissa / significant value f from the normalized value we found earlier. So we just copy that down. We can note that this value is going to be our mantissa f. So then f is equal to just this part. And that's all for step 4. And then step 5 is just to put it all together. So the sign bit 64.2 is positive, so the sign bit should be 0. E will be that 8-bit representation of our biased 127 value of the true exponent 6, so that's going to be 1, 0, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0. And then f, which we just found, will be this value right here. And so that's how we convert 64.2 from decimal to IEEE 754 single precision.